Before I jump into the problems for section 6.2, I should probably introduce a topic or an idea called one-to-one functions. And it's a pretty simple idea, but probably should try to define it. So a function is either one-to-one or not one-to-one. And I should maybe just make a little table here. So this would be a characteristic of a one-to-one function. I'll put them in the left column. And then characteristics of a not one-to-one functions. A one-to-one function, every point has a unique y, which means no two points have the same y. So if in a function every single point has a different y, then that function's a one-to-one function. To be a not one-to-one function, we could have two or more points have the same y. I don't know if this is the greatest explanation, but it's going to get us through the section just fine. So if I look at a function and I could see a list of points for a function, then it's easy to pick if a function is one-to-one or not. So here's a function f. I'm going to define it as a one-to-one function. I'm just going to create it as a set of points. So maybe I'll make the point 0, 1, 1, 3, 4, 5. Just a simple 3-point defined function. And this is a one-to-one function specifically because no points have the same y. In this column of my not one-to-one functions, if I create another function, I don't know if I can get 4 points in here, but if I did like 0, 1, 1, 3, and 4, 1, then that's a non-one-to-one function because we have multiple points that have the same y. If you're thinking about duplicate x's, if a function is written as a set of a function can't have duplicate x's. If there's duplicate x's, then the relation, this is a relation, relations are only functions if all the x's are different. So that's kind of the first characteristic of a one-to-one function, that every point has unique y, which means no two points have the same y. If two or more points have the same y, that's not one-to-one. And graphically, a one-to-one function, we say it passes the horizontal line test. And this means that every possible, or is impossible, how about that? It is impossible to draw a horizontal line that touches the graph in more than one place. The graph of the function in more than one place. And then for the not one-to-one, functions are not one-to-one if they fail the horizontal line test. Which means it is possible to draw a horizontal line that touches the graph in more than one place. And I should do a quick example of that before I jump into the section. Which means I need to yank out some graph paper. So I'm going to draw an example of a one-to-one function. This will be a one-to-one function. Something like, well, I guess this is upside down. A one-to-one function might be something like this. That would be an example of a one-to-one function because no matter what horizontal line I draw, a line parallel to the x-axis, it's impossible to draw a horizontal line to touch the graph in more than one place. Every line that's parallel to the x-axis, every horizontal line will only touch this graph in one place. So this is an example of a one-to-one function because it passes the horizontal line test. The other side of this, the failing the horizontal line test, I'll draw an example of a not one-to-one function. I'll just draw a nice parabola. So this is an example of a function that's not one-to-one because it fails the horizontal line test. There's lots of horizontal lines that I can draw that touch the graph in more than one place. So this is immediately not one-to-one. And if you look at my explanation to the first category for one-to-one, the first category says we're not one-to-one if two or more points have the same y. And failing the horizontal line test is equivalent to the first explanation because when you draw a horizontal line, every place it touches the graph is a point on the graph. Here, this graph has the point -3, +7, and that point's the point +3, +7. When a graph fails the horizontal line test, the places it touches the graph are 2 points, 2 different points on the graph that have the same y. Like this line down here goes through the point -2, +4, and +2, +4. What I've created are 2 sets of points that have the same y. So there are 2 points that have y equal to 7. There are 2 points that have y equal to 4. And anytime on a graph or in a function, if you have multiple points with the same y, the graph is not one-to-one. So these tests, the looking for 2 points that have the same y to make a function not one-to-one, is equivalent to failing the horizontal line test. So the first bunch of problems in section 6.2 just get us used to these concepts of one-to-one and not one-to-one. And the first 4 problems give me graphs and ask the question, is the function one-to-one or not? And it says use the horizontal line test to say whether the function is one-to-one or not. For each one of these problems, my answer is going to be either the function is one-to-one or it's not one-to-one. And it's not one-to-one if it fails a horizontal line test. It is one-to-one if it passes a horizontal line test. I'm not sure that the graphs in 3 and 4 show up so well, so I'll darken them up before I do it. When I go to do my problem 1 or problem 2 fails the horizontal line test because it's possible to draw a horizontal line to touch the graph in more than one place. My answer to problem 2, I'd say this is not a one-to-one function. I'll just say this is not one-to-one. One-to-one, I guess, means 1x for 1y, or I guess that's probably the best way to think of it. The function that's drawn in problem 4 looks like this, and the function that's drawn in problem 3 looks like this. Just because my graph gets so close to the axis, you couldn't tell them apart. the axis in the graph. And when I try to determine whether 4 is 1 to 1, no matter where I draw my horizontal line, it's only going to touch the graph once. So none of these horizontal lines clearly touch the graph in more than one place. So we'll say this graph is 1 to 1. So you should be able to do 1 and 3 with that kind of motivation. The next few problems give us functions, and it would be nice if we're staring at a function to be able to tell whether the function is 1 to 1 or not. And it's pretty easy to tell if you can get a graph of a function that it is 1 to 1 or not 1 to 1. So that's what my instructions for 5 through 12 suggest. Use a graphing calculator, sketch a graph, and then answer whether any of these are 1 to 1 or not. And let me just do problem 6 real quickly. There's no algebra to do here. For problem 6, I'm going to graph the function x plus 3. And I'm just going to hit zoom standard. I have no idea what my window is at right now. When you do your homework, you don't necessarily have to copy the graph. But the graph for number 3, I can copy this. It goes through 3 on the y-axis, because the b is a 3 and it's a line, and that's the b, and it looks something like this. I could graph it more accurately using the slope. But that's a picture of the function, and it clearly passes the horizontal line test because it's impossible to draw a horizontal line to touch the graph in more than one place. So my answer to problem 6 is going to be this is 1 to 1. When I jump down to do problem 8, this function y equals clear parentheses x minus 3 squared plus 6. It's going to be a parabola, and parabolas most definitely are not 1 to 1. But let me go ahead and graph this by hitting my graph button. What I see is just a little hump of the graph here, but that's enough for me to know it's not 1 to 1 because the graph clearly fails the horizontal line test. So this means the graph is not, my answer is going to be not 1 to 1. If I wanted to, I could peek at the table. I don't have to, but if I peek at the table, you'll start to see in the y column, I see y equal to 7. I see the point 27. I see the point 47. Those are 2 points that have the same y of 7. I see the point 110. I see the point 510. Those are 2 points that have the same y equal to 10. If you see duplicates in the y column, when the function on the table, the function is also not 1 to 1 because those are all points that have the same y's. Similarly, what I drew here, those 2 places where the graph, my horizontal line touches the graph, are 2 points that have the same y. Parabolas are never 1 to 1. Lines are always 1 to 1. So I kind of knew that if a graph doesn't kind of turn directions or have a bend in it, it can't be. It has to be 1 to 1. If a graph has a big bend in it where it changes directions, it's not going to be 1 to 1. So I'm going to give number 10 a go. I imagine this graph looks like a parabola. So when I go to do number 10, clear y equals x up arrow 4 minus 3, hit my graph button. It's just a flatter parabola, if that even is a proper description. This is going to be clearly not 1 to 1, which means if I peek at the table, in the y column I'll see duplicate y's. So I see, here I see a y of 13, there I see a y of 13, there I see a -2 and another -2. When you get duplicate y's in a table, the graph isn't 1 to 1. Similarly, when the graph fails the horizontal line test, it's not 1 to 1. The cubes are a little bit tricky. Cubes are usually 1 to 1, but not always 1 to 1, and it's really hard sometimes to look at a graph of a cube around where it bends to see if it's 1 to 1 or not. When I look at the graph that my calculator gave me for problem 12, it looks more or less like this. And clearly up here, there's no way to touch the graph with a horizontal line in more than one place. The question would be around there if it's possible, and it's not supposed to be possible. If I peek at my table, in my table, I look at the y's, -3, -2, -1, 6, 25. I don't see any duplicate y's. Because I don't see any duplicate y's in my table, and I think that it looks like the graph passes a horizontal line test, I'll say this graph is 1-to-1. But right there, some students will think maybe a line right through where it has that little bend, it might be possible to draw a horizontal line to touch the graph in more than one place. If I really condense my window, maybe made my window -1 to 1 and -3 to -2, this will blow up this part of the graph, and you'll see better that, or a little bit better, that it's not 1-to-1, I guess. How about if I made it like -1 or -2 to 2 and -4 to 4? I don't know. That's blowing up this region a little bit. And right there, the graph is still, it's always going up. The graph would have to go up and then come back down to have it be not 1-to-1. So these cubes are supposed to be 1-to-1, even though it's maybe a little deceptive. So my answer for problem 12 is going to be it is 1-to-1. The next few problems, 13 through 18, give me functions that are defined as a set of points, and it asks me two things. The first part, it says, determine if a function is 1-to-1 or not. We should know how to do that. And then it introduces a new concept. It says, if a function is 1-to-1, find its inverse. So real quickly, for my problem 14 and my problem 16, I'm going to figure out if the functions are 1-to-1 or not, and then I'll talk about the inverse after I've got that part done. So for each one of these problems, the first thing I need to do is determine whether it's 1-to-1 or not. Problem 14 is not 1-to-1 because it has 2 points that have the same y. Problem 16 is 1-to-1 because the 4 points have y's of 4, 6, -3, and 0, and all the y's are different. So where 14 is not 1-to-1, 16 is 1-to-1. My instructions say first determine whether the function is 1-to-1 or not. I did that for both problems 14 and 16 by just looking at the y's. Duplicate y's are not 1-to-1. All unique y's, it is 1-to-1. And then it says if a function is 1-to-1, find its inverse. So here I'm finished with this problem because the second sentence says if a function is 1-to-1, do this extra thing, find the inverse. And because 14 is not 1-to-1, I'm finished. I don't have to find the inverse. 16, because I have a 1-to-1 function, I need to find an inverse, and it's super easy to do. So I need to find, because it is 1-to-1, the inverse of k. Super easy to find an inverse, and there's a notation I need to do. The inverse of k is going to be the set of points of k completely reversed. So the point -3, +4 is a point in k. To find the inverse of k, I'm going to flip that to the point 4, -3. I'm just going to flop the x and y. The point -5, 6 is in k. The point 6, -5 is going to be in the inverse of k. The point 9, -3 is in k. The point -3, 9 is going to be a point in the inverse of k. And the point 4, 0 is in k. The point 0, 4 is going to be in the inverse of k. So this right here is the inverse of k equals this function that has this set of points. This is not the best way to write my answer. Using the words the inverse of k can be replaced by a symbol. So I've done everything I needed to do for these problems. I determined that this wasn't one-to-one, so I didn't find its inverse. I determined that this was one-to-one, so I found its inverse by switching the x's and y's. But I wrote my answer in a not very slick fashion. There's a symbol that you can attach to a function so that somebody that reads mathematics knows that it's the inverse. And these whole words, the inverse of k, is equivalent to that symbol. So when I look at this symbol right here, I read this as the inverse of k equals, and a better way to finish up problem 16 would use the symbol k with a -1 exponent, and in function notation, that -1 exponent we read as the inverse of. So completely done with 16, completely done with 14. The reason we don't find the inverse of g, because if you switch the points around, if you switch it to the point 2, 3, the point 5, 4, the point 4, -3, the point 5, 1, and the point 6, 0, if you found the inverse of g, it wouldn't be a function, because to be a function, every point has to have a different x. If you have 2 points that have the same x, that's not a function. So because the inverse of g isn't a function, it wouldn't be right to find the inverse and give it function notation. Where here, when I do the inverse of k, because every point has a unique x, the inverse of k is a function, so that makes sense to find it inverse. So 2 more problems for this grouping. Your problem 17, my problem 18. When I look to answer the first part, whether this function n is 1-to-1 or not, I look at the y's. If all the y's are different, it is 1-to-1. So the first part of my answer to 18, I'm going to say n is a 1-to-1 function. I could just say it is 1-to-1, but this is being maybe more accurate. Because it is a 1-to-1 function, I need to find its inverse. The nicest way to find the inverse is just to take each point and switch its x and its y. Well, the first 2 points, they're not going to look different. When I flip these points around, you still get the point 1, 1. That still becomes the point 2, 2. This point's going to change because I'm going to flip the x and y and get the point 4, 3. And this point's not going to look any different. It's going to look as the point 5, 5. So I found the inverse. I said it was a 1-to-1 function. I found the inverse. And next to the function, I'm going to write something so that somebody that reads mathematics knows that these 2 functions are related, that n and inverse are related. And how they're related is all the x's and y's are switched. So I would read this as the function n has the points 1, 1, 2, 2, 3, 4, and 5, 5. The function n inverse, or the inverse of n, has the points 1, 1, 2, 2, 4, 3, and 5, 5. So completely done with that bank of problems. The next bank is just as easy, but a little bit more work. So in each of the problems between 19 and 26, I give you the graph of a 1-to-1 function, meaning the graphs pass the horizontal line test. I'm asked to draw the graph of the inverse function. So in problem 20, the graph of f of x is given, and I need to graph, I'll do it in red, for number 20, I need to sketch a graph of f inverse of x. Super easy to do because inverses of a graph have the exact same shape as the given graph. Because my graph in problem 20 is a line, when I graph f inverse, it also has to be a line. The nice thing about the way I've done these for you, the function that I drew, I labeled some points, and in problem 20, I labeled the points of f of x being 1, 5, 0, 1, -1, -3. Well, automatically, I know that my graph of f inverse has to have the points 5, 1, 1, 0, and -3, -1, because inverses have their x's and y's switched. So what I'm going to do to graph the inverse is I'm going to take any point that I'm giving you on the graph that I'm creating the inverse from, and I'm going to flip its points, and then I'm going to plot those points. So first I'm going to plot the point 5, 1, then I'm going to plot the point 1, 0, and then I'm going to plot the point -3, -1. And what I'm going to do is I'm going to connect those points. I'm going to connect those points with the same shape that the initial graph has. So this initial graph has a shape of a line. So the same shape of a line is another line. So I claim that this is a graph of an inverse. I'm done, other than maybe it might help you to understand, this is the best one to do. Yeah, I think so. So how could I tell my answer is right other than it is? Because I've switched all the points and debating on whether to say something more or not. I probably should. Graphs of inverses are symmetric to the line that goes through the origin that passes through the points 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. If I take the time on this graph to graph a line that goes through the point 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, -1, -1, -2, -2, -3, -3, -4, -4, -5, -5. The line that goes through the origin, that goes through every point where the x and the y are the exact same number, is the line of symmetry, meaning that on either side of this line, if I've graphed my inverse properly, you'd get a mirror image. So above this line, there's a reflection below this line that has a mirror image, and similarly here. I'm not the most visual person, but a line that goes through the origin that passes through, this is a line y equal to x for what that's worth, a line that goes through the origin that passes through every point where the x and the y are the same, which is a line y equal to x, will serve as a line of symmetry that on either side of that line you get a mirrored image for what that's worth. Not the most visual, but sometimes that helps. The only thing that you have to do is find the points of the inverse, plot the points of the inverse, and graph them with the same shape that the original line has to properly graph an inverse. Both 21 and 22, my graph is a line, so when I go to do the points for my inverse and graph my inverse, I'm going to create a line. So my points for my f inverse function in my particular graph are going to have the points 6, -1, 2, 0, and -2, 1. Because the initial function is a line, my inverse is going to graph to be a line. So let me go ahead and graph the point 6, -1, 2, 0, and -2, +1. And I'm going to connect those 3 points with a line because the initial function is a line. And I'll say I'll successfully have graphed the inverse of this function. So the best I can. This would be a graph of f inverse. That's all that needs to be done for problem 22. This is the graph of f inverse. That's all I was asked to do. I was asked to graph the inverse of f. If I wanted to get an idea if my graph is correct, I would just plot the line that goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, -1, -1, -2, -2, -3, -3, -4, -4. And that line right there is supposed to create mirrored images on either side of that line. So how can I see that so well? I can't see that so well at all. These two lines, these parts right here, this is above that line, this is below the line, this is the reflection of this, of cross-section of this across that line is that. If you're more visual than me, that looks completely obvious to you. If you're not that visual, like I'm not that visual, I don't see this so well that this is the mirrored image of that across that line, and this is the mirrored image of that across that line, but it is the case. All right, now the ugly ones. So 23 and 24 are a graph of a cube, and it got so ugly when I tried to write the points on here that I just made dots. I made dots and I wrote what the points were. So I'm going to create the points of my inverse by switching the x's and y's and plotting them. The first point, -2, +8, is that point in problem 24. My inverse is going to have the point 8, -2. That's going to be an easy point to graph. So over 8 down 2, that's an easy point to graph. The second point right here, that's the point -1/2, +1/8. My inverse is going to have the point +1/8, -1/2. That's a little bit tricky. +1/8 is just to the right of the x-axis, and -1/2 is going to be there. The next point, that's the point +1/2, -1/8. My inverse is going to have the point -1/8, +1/2. -1/8 is just to the left of the origin, and then up 1/2, maybe about there. And then the last point, there's the point +2, -8. My inverse is going to have the point -8, +2. And the point -8, +2 is going to be there. And I'm going to connect it with the same sort of S-y kind of shape. So I'm going to connect these points. Try to connect those points with the same S kind of shape. And same deal, I can draw a line that goes through the points 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, -2, -2, -3, -3, to kind of convince myself that my inverse is correctly drawn, because on either side of that line I'm going to get like a mirrored image. So this piece right here, it's mirrored images there across that line. This piece right here, it's mirrored images there across that line. So the inverse of a cube, or an S-type function, has that same squiggle shape and goes through the points with all the x's and y's flipped. So your problem 23 is super similar. When I go to do my problem 26, the initial function in problem 26 has the points 0, 0, 1, -1, 4, -2, and 9, -3. That's the f of x function that's given. I'm drawing f inverse of x, and f inverse of x has to have the point 0, 0, which I already have plotted, -1, 1, so -1, 1, which is there, -2, 4, which is here, and -3, 9, which is here. Because the original graph is kind of a half parabola on its side, its inverse is going to be a half parabola on its side. So I'm just going to connect those points that I created in the inverse with a half parabola on its side, and that's all I have to do. I don't have to draw the line that goes through the origin, that goes through the points 1, 1, 2, 2, 3, 3, 4, 4, which is a line y equal to x, to confirm that I have the inverse correct. I can just graph the inverse and be done with that. All right. 27 through 36. 27 through 36 give me functions that are one-to-one, which means they have inverses. I need to figure out how to find the inverse of a function if I don't have a set of points. And it's not terribly hard to do. So for problem 28a, I'm going to go and I'm going to find the inverse of the function 3x minus 6, which is a function where all the x's and y's would be switched. So let me try to do that. So for problem 28a, the function that's given is f of x equals 3x minus 6. And what I need to do is find the inverse and express it using inverse notation. And the inverse notation that I'm going to express my answer with, or the appropriate notation that I'm going to express my answer with for the f function, the inverse notation I'm going to express it with is that. So how do I find an inverse? It's just a series of a few pretty basic steps. The first steps to find my inverse is to change the function symbol to y. So I don't have a set of points. So I'm going to have to follow some steps to find the inverse when a function is given in function notation. The first step is going to be to change the function symbol to the letter y. That's not really any algebra, and that's just going to make my algebra easier to do. So first step, the function symbol in problem 28a is this f of x. I'm going to change that function symbol to the letter y and rewrite this as y equals 3x minus 6. That hasn't created an inverse, but it'll make it more obvious when I do create the inverse. Step 2 is I'm going to create the inverse. And I create the inverse by switching the x and the y. So I'm going to go x equals 3y minus 6. I'm actually done, but it's rare to have a function not solve for y. So I'm going to do some algebra and solve this for y. So my step 3 is going to be to solve for y. And there's some flexibility here when I go to solve for y in terms of how I write my answer. I'm going to add 6 to both sides and divide both sides by 3. So I'm going to get x plus 6 equals to 3y. And then I'm going to divide everything by 3. The safest way to do this would be divide every letter and every number by 3 to solve for y. And if I do this, I'm going to get x over 3 plus 2 equal to y. I could have, when I got to this point right here, where I had x plus 6 equal to 3y, I could have made one big fraction on the left-hand side and wrote x plus 6 all over 3 equals to y. If you make one big fraction, you have to be real careful because usually you can't reduce. You couldn't, if you had one big fraction, divide the 6 over the 3 because you'd be stealing it away from the x when you can't. This is a safer way to do solving for y. When you're just dividing, you'll just divide every number and every letter to get the y solved for. And lastly, I'm going to replace the y with the inverse notation, the function inverse notation, and I'll have my answer. So I'm going to write, in place of y, I'm going to write the inverse of x, inverse of f, equals, and I'm going to write the y on the left-hand side just because it's going to be easier for me to do it that way. It's the way usually functions are written to the left of the equal sign. That's technically everything done for 28a. 28a asked me to find the inverse and express it in function notation. So I took the original function, I changed the function symbol to a y, I switched the x and the y, and I solved for y. So it's just really 3 steps, and then the last step's a non-algebra step. And in fact, 3 of the 4 steps are non-algebra. Changing the function to y is non-algebra, switching the x and y is non-algebra, solving for y is algebra, and then changing from y notation to function inverse notation is not algebra either. Done with 28a, I found the inverse. Now I want to see if my answer is right. Let me sneak and do 28 part C first. So for those of you that are visual, there's a visual way to check to see if your answer is right. So in problem 28, the function that was given to me was f of x equals 3x minus 6, and the inverse that I came up with equals x divided by 3 plus 2. If you're super visual, you can graph both of these and the graph that goes through 1, 1, 2, 2, 3, 3, and 4, 4 all simultaneously on the same graph, and you might be able to justify to yourself that your answer is right. So let me try to do that. Let me graph y equals 3x minus 6, and then y equals to x divided by 3 over plus 2. and the 45-degree line that goes to the origin, y equals to x, all simultaneously with a standard window. So that's the graph of 3x minus 6. There's the graph of the inverse, and there's the graph of the 45-degree line that goes through the origin. It looks to me like the top part has a mirrored image on the bottom, and similarly, you can see, I think visually, I can see that my inverse is correct, because it looks like that those two graphs, the graph of the original function, the graph of the inverse, are mirrored images across the line y equal to x. So visually, I feel my answer is correct. So that's what part C of 28 asks me to do. It says, use your calculator to graph the function and its inverse and the line y equals x on the same coordinate system. This is just a visual confirmation that you calculated the correct inverses, because inverses should be mirrored images across that line that goes through the origin. There's nothing to write down for part C. This is just for your peace of mind. Just go, hey, I think I have the right answer because the graph seems to have a mirrored image across that line y equal to x. There's a horrible part B that we have to do. And for part B, there's an or. Let me just do the first part of this because I don't need to do part of it. To know that for certain your inverse is correct, you have to find f composed with f inverse of x, and it has to be equal to x. So when I go to do part 28b, I need to check to confirm I have the correct answer. To part A by finding f composed of f inverse of x. My answer is correct. My answer to part A is correct if this comes out to be exactly x. If f composed with f inverse of x equals x, and my answer is wrong, if f composed of f inverse of x equals anything other than just a single x. So 28b and the part B's for these next problems are essentially proofs. And the proof is just finding f composed with f inverse of x, and we know how to do that because we did that in the last section. So in 28b, I have the function f of x equals 3x minus 6, and the function f inverse of x equals to x over 3 plus 2. To do 28b, I just need to find, I don't know if I have enough room here, f composed with f inverse of x. And I know that that means to find f of f inverse of x, which means in the f function, I'm going to change the x to x inverse. That's going to be 3 times f inverse of x minus 6, because to find f of anything, you change the x to what's in the parentheses. So to find f composed of f inverse, which is the same as f of f inverse, I'm going to do 3 times f inverse of x minus 6. And now I'm going to change the f inverse to what it's equal to. So this is going to equal to 3 times x over 3 plus 2 minus 6. That's just changing that f inverse to x over 3 plus 2. And now I'm going to clear the parentheses. I'm going to go 3 times x over 3 plus 3 times 2, distributing through the parentheses, and I have the minus 6. In the first multiplication, the 3's cancel, and I get an x. The second multiplication gives me a plus 6. The third, I still have the minus 6. The plus 6 and the minus 6 cancel, and I get just a naked x. So I know that my answer to part A is right, and I'm actually done with part B. My answer to part A is right if I find f composed with f inverse of x and it equals to x. My answer to part A is wrong if I find f composed with f inverse of x and it equals anything other than x. Because I just found f composed with f inverse of x by finding f inverse of x and doing the algebra, because it came out to x, I've checked my answer and I know my answer is correct. If this algebra would have produced something other than just the single letter x, my answer would not be correct. Alright, so I'm going to move on and do less explaining and more computating when I do problem 30. So give 27 a go, and I'm going to go through each of the parts of 30 with a little less theory, just a little more just this is what we need to do. So problem 30 gives me the function, horrible fraction, f of x equals to 2x minus 5 over 7. When I jump into 30 part A, I'm going to find the inverse. So to find the inverse of x, f of x, I need to do the steps. So first step, change from function notation to the letter y. So that function notation in problem 30, I'm going to change to the letter y. So I'm going to get y equals 2x minus 5 over 7. 2, I'm actually going to create the inverse. I'm going to switch the x and the y. That's going to give me x equals 2y minus 5 over 7. Now to the algebra stage. The algebra stage is the solve for y, and this is where it requires being clever. How do I solve for y? Well, I'm going to set this up to solve by cross multiplying. I'm going to write both sides as a fraction and cross multiply. The right side's already a fraction, so there's no work to do to it. The left side, I can make it a fraction by writing it over 1. And now I'm going to cross multiply both ways, and it doesn't matter what I write on each side. Probably helps to have the y on the left hand side. So I'm going to cross multiply up and cross multiply down and get 1 times 2y minus 5 equals 7 times x. That's going to give me 2y minus 5 equals 7x. Now I'm going to add 5 to both sides and then divide by 2. So this is going to give me 2y equals 7x plus 5. And then I'm going to divide each number individually by 2 just because it makes students make less mistakes. But I could make a big fraction with 1, 2 on the right hand side as well. So I'm going to write y equals 7x over 2 plus 5 halves. Once I have the y solved for, I'm done with step 3. Moving on to the last step, step 4, replace the y with the inverse symbol. Because the function is f, I'm going to replace it with the symbol f inverse of x. So I'm going to write f inverse of x equals 7x over 2 plus 5 halves. That's my answer to part A of number 30. So for 30A, f inverse of x equals 7x over 2 plus 5 halves. I'm going to jump down and do C because that's just pressing buttons, and pressing buttons I can do quickly. So to visually see if my answer seems reasonable, I'm going to graph all 3 functions. So I'm going to clear out all the junk that's in here. I'm going to graph the f function, 2x minus 5 divided by 7. I'm going to graph 7x divided by 2 plus 5 divided by 2. And I'm going to graph the line y equal to x. All all in the same graph. I didn't do a y1. I guess it doesn't matter. There's the initial function. Second comes my inverse. And there's the line that goes right through the origin. One goes through 1, 1, 2, 2, 3, 3, and 4, 4. And that looks like that is a perfect symmetry. It looks like there's a mirrored image on either side of that line. So I think my answer is more than likely right. So I'm just going to say for this one, C calculator, we don't have to do any extra writing. I just want to confirm this on my calculator. And then part B has a choice. You can do F composed of F inverse, or you can do F inverse composed with F. I'm just for all of these going to do, even though they both are proper checks, I'm going to find F composed with F inverse. If it comes out to be just X, I'll be happy with my answer. So to do part B, I really should just say find F composed with F inverse of X. That's easy enough to do because that's just F of F inverse of X. So into that F function, I'm going to change the X to F inverse. So this is going to be 2 times F inverse of X minus 5 over 7, because all I have to do is in the F function change the X to F inverse of X. Now I'm going to clean that up and get rid of that ugly function notation. So in this numerator here, instead of writing F inverse of X, I'm going to write what it equals to. So I'm going to go 2 times and then minus 5 over 7, and I'm going to change, the only thing I'm going to change is that to 7x over 2 plus 5 over 2. Now I'm going to work on that numerator for part B to get my answer that I need to get of just plain X. So I'm going to go F composed with F inverse of X. I'm going to do this multiplication, which is 2 times 7x over 2, and this multiplication, which is 2 times 5 halves, then minus 5 over 7. So I've cleared my parentheses, and now I'm going to do the algebra that's needed here. These 2's are going to cancel, and those 2's are going to cancel, which is going to clean my numerator up. I'm going to get F composed of F inverse of X equals, that's going to turn into a 7x. That's going to turn into a plus 5 because the fraction is going to cancel. Then I have a minus 5 all over 7. The 5's cancel, and I get F composed of F inverse of X equals to 7x over 7. The 7's cancel, and the only way my answer to part A is right is if when I find F composed with F inverse, if it just comes out to plain ordinary X. If it came out to something that wasn't just a perfect X, then my answer to part A would be wrong. So my answer, my work for part B is just simply finding F composed with F inverse of X, which we did a couple times in section 6.1, just because I knew this was coming up in this section. If your answer comes out to X, you're checked properly and you know your answer to part A is right algebraically. Part C is just guessing your answer is right visually. Alright, so give 29 a go. We have like 3 more problems each to do. So 31 and 32 are tricky problems. So let me do part A to find the inverse. So as I work through problem 32, part A, I'm going to find the inverse. So for 32A, the first thing I'm going to do is change the function notation to the letter y. So I'm going to write y equal to 3 over x. So I'm doing the steps without writing them down. First step in finding an inverse, change the function notation to the letter y. Second step in finding an inverse is switch the x and the y. So I'm going to get x equals 3 over y. Last step is to solve for y. So here I changed f of x to y. Here I switch the x and y. And now I'm going to solve for y. And just like the last problem, I'm going to solve by cross multiplying. So I'm going to write the x side as a fraction, and I set it up to cross multiply. This will give me xy equals 1 times 3, or xy equals to 3, and then I'll divide both sides by x and get a really surprising result that this function is its own inverse. Done with step 3. Now I'm going to replace the y with the f inverse symbol. And that's going to be my answer to 32a. The inverse of the function 3 over x is its own inverse, which is really remarkable. So done with part A, I found the inverse. The inverse of the function f inverse of x equals 3 over x. It's going to be hard to graph this, but I'm going to do part C real quickly on my calculator. So I'm just going to say C calculator. And the more visual you are, the more you'll understand that this is correct. The less visual you are, the more you'll be in my boat that you need to do the algebra to know your answer is correct. So there's the f function, there's the inverse, there's going to be the line that goes through the origin. And when it graphs it, you can see on either side of this line, above this line and below this line, there's a mirrored image on either for the two pieces of the graph. So visually you can see mirrored images of the graph on either side of the line y equal x. So I feel my answer is more than likely correct. Now I'm going to move on to part B. And for part B, I'm going to find f composed with f inverse. And it better just equal x. So I need to find, for 32b, I need to find f composed with f inverse of x. I know that that means f of f inverse of x. That means to go to the f function, change that x to f inverse. So that's going to be 3 over f inverse of x. Just changing the x to f inverse. And now I can change f inverse to 3 over x. So this is going to be 3 over 3 over x, just changing that to what it's equal to. And now I just need to simplify this. And this is deceptively easy. This is going to be f composed with f inverse of x equals 3. And these 3 layered fractions I don't like, so I'm going to write it with a division sign. I change that fraction to a division sign. Dividing by a fraction is the same as multiplying by the reciprocal. So I'm going to rewrite this as 3 times x over 3. And then the 3's are going to cancel. And you're going to be left with f composed with f inverse of x equals to just that x. And that's what has to happen. For my only way my answer to part A is right is if the graph has a mirrored image on either side of the line y equal to x, which is a line that goes through 1, 1, 2, 2, 3, 3, and 4, 4. And if f composed with f inverse equals just x. If this computation would have came out to anything other than identically x, my answer to part A wouldn't be right. All right, so give 31 a go. And we just have 2 more problems to do. Usually, if the function's a cube root, the inverse of a cube root is a cube. So when I go to do problem 34, usually the inverse of a cube root, which this problem is a cube. So in my answer, I'm going to expect to see an x cubed when I go to find the inverse. And conversely, the inverse of a cube is a cube root normally. So when I go to do part A of number 34, I'm going to try to find the inverse of the function. So to do 34a, I take my function, f of x equals the cube root of x minus 2, and I'm going to replace the f of x with a y, and get y equals the cube root of x minus 2. I'm going to switch the x and the y and get x equals the cube root of y minus 2, and then the ugly algebra of solving for y. It's really actually easy algebra. I'm going to cube both sides, and when you cube a cube root, the cube cancels out the cube root. So on the right hand side, when I cube it, I'm going to just get y minus 2. On the left hand side, when I cube it, I get x cubed. So this gives me x cubed equals y minus 2. I'm going to add 2 to both sides and get x cubed plus 2 equal to y. I'm done solving for y. I'm now going to replace the y with f inverse. So I'm going to write f inverse of x equals x cubed plus 2. Done with part A. I'm going to move on to the part C and see on my calculator if that answer seems reasonable. But the inverse of a cube root is usually a cube, and I come up with a cube here. So my answer to part A, f inverse of x equals x cubed plus 2. So I'm going to graph all of these to do my part C. And again, I'm not going to write anything down on my part C. I'm just going to say, see my calculator. And so when I do this, I'll go y equals clear, clear. First one, to get the cube root, you hit the math key, and you go down to option 4 for cube root, and then x minus 2. And then the next thing I need to graph is x up arrow 3 plus 2, and then the x. So first graph is the cubed root. Second graph is the cube. And now the line that goes through the origin, and that's beautiful. I could actually even see that symmetry, that above and below this line, you have perfect symmetry. So I believe my answer is correct. That's not enough to guarantee it's correct because the graph can play tricks on you. So I need to do the part B. And for the part B, I'm just finding f composed with f inverse of x. That's the slickest way to show that your answer is right. So moving on to part B. For part B of 34, I need to find f composed with f inverse of x. And to do that, f composed with f inverse of x f composed with f inverse of x equals f of f inverse of x. That means in my f function, I need to change that x to an f inverse. So that's going to be the cube root of f inverse of x minus 2. Just took that x, changed it to that x, f inverse. Now I'm going to go f composed with f inverse of x equals 2, and I'm going to change that to x cubed plus 2. So it's going to be the cube root of x cubed plus 2. That's changing that to x cubed plus 2, and I still have the minus 2. Under the radical now, the 2's cancel. I get f composed of f inverse of x equals 2, the cube root of x cubed. And cubes cancel out cube roots cancel out cubes, so these are all going to cancel, and I'm going to get just that lonely x that I need to get. And that's what has to happen in every part B if you find f composed with f inverse. If your answer to part A is right, you get just a plain, exact, ordinary x. Alright, so you have 33 to do. So pause the video and give it a go. And I will do 36. 6 and 35 want me to find inverses of cubes. And inverses of cubes are usually cube roots. It's a cube because it has an exponent of 3. And I expect to see a cube root in my answer for the inverse. So in 36 part A, as I go to find the inverse, I just go through the steps. The first step I'm going to do is change the function symbol to the letter y and get y equals x cubed minus 3. Second, I'm going to switch the x and y and get x equals to y cubed minus 3. Third, I'm going to solve for y. I'm going to add 3 to both sides and get x plus 3 equals y cubed. And then I'm going to cube root both sides. On the left side, cube and cube rooting cancel each other out. And on the right-hand side, nothing simplifies. So I get the cube root of x plus 3 equals to y. So I've done all my steps. Step 1, change to y from the function notation. Step 2, switch the x and y. Step 3, solve for y. And then step 4, introduce the function inverse notation. So I'm going to get f inverse of x is the cube root of x plus 3. That's my answer to part A of 36. Let me do part C. I'll just say C calculator. There's nothing to write down here. It's silly to copy a graph when you can just look at it. So I'm going to graph y equals x cubed minus 3, and then math cube root of x plus 3, and then y equal to x. Hit my graph button and hopefully see the symmetry that I expect to see. And for some reason on cubes I could see that symmetry so nicely. Generally I can't. So that looks perfect that you have that mirrored image on either side of that diagonal line through the origin. So I feel good about my answer. I'm going to finish up to check, find f composed with f inverse of x, and it has to equal just x. So as I move on to part B of 36, I need to find f composed with f inverse of x, which is f of f inverse of x, which means in the f function to change that x to x inverse. So it's going to be f inverse of x cubed minus 3. That's just changing that x to an x inverse. On my next line, I'm going to change that to the cube root of x plus 3. So inside that parentheses, where I have the f inverse symbol, I'm going to change it to the cube root of x plus 3. The algebra is super easy because cubes cancel out cube roots, makes it so I don't even need that parentheses. This gives me f composed with f inverse of x equals x plus 3 minus 3. The 3's cancel, and the only way I know my answer for part A is guaranteed to be correct is if I do this computation and it equals exactly x. If it equals something other than exactly x, then my answer to part A isn't right. Alright, so that's a little bit longer than I wanted the video to be, but this kind of is what it is, but at least it's only one part.